All right, so here we are. It's section 2.4 where we're going to be talking about the exponential family. Now, in the previous video, I tried to justify why we might be interested in this family. And in this particular section, the beginning part that we're going to discuss today, we're just going to show how some of the simple probability distributions that we work with so far fall into this family. And the basic game is to show that our normal parameterization of these distributions can be written in this particular form. And remember what this form was? So we had the probability of the data given the parameters, and the form was that this probability distribution was a product of a function that depended only on the data, another function that depended only on the parameters. It's kind of a normalizing function basically, which is going to be quite important. And then inside an exponential, the parameters interacted with the data, but not directly, instead via this function u of x. And we'll find out later, if we haven't already mentioned it, that this is what's called a sufficient statistic. And it's going to be important because we're going to be interested in estimating the parameters, the value of the parameters given the data. And we'll find that when we're doing that, what's going to matter, the property of the data that's going to matter is this function, because that's how the data is going to interact with the parameter we're interested in. But we'll see that later. So the whole game today is just going to be working using a couple of examples of simple distributions and showing that they're actually part of this family. Because you'll remember that one of the cool things about this family was that lots of the distributions that we actually work with are actually members of the family. So we're just going to show that for a couple of examples. Okay, so let's see if there's a couple of points we should just remind ourselves from before. So x may be scalar or vector, may be discrete or continuous. So again, part of how general this family is. H are called the natural parameters of the distribution. And you'll see in a couple of examples that those parameters aren't necessarily our default parameterization. There'll be some function of that sometimes. And ux is some function of x. The function g of eta can be interpreted as a coefficient that ensures the distribution is normalized. So this is kind of why we call it normalizing, the normalizing function. Okay, so let's just look at the very first example. So we begin by taking some examples of distributions introduced earlier and showing that they are indeed members of the exponential family. Okay, so consider the Bernoulli distribution. I remember this distribution was, essentially the tail flip, the coin flip distribution, right? So what is the probability of heads, given that the coin itself has some probability mu of turning heads. Okay, and we remember that from there we are, one of our parameterizations was this, right? And x here is going to be a binary random variable. So if x is 1, well, then mu will come out. So you can say the probability of, x being heads will just be mu, because this term here will be 1 minus x will be 1 minus 1, which is 0, which will eliminate that. So the probability of x equals 1 is going to be mu, and the probability of x equal to 0 will just be 1 minus mu. So exactly what you would expect for a coin toss. Okay, so this is kind of one way that, one compact way of writing it. And now the game is going to be to try to write this in this form. And how are we going to do that? Well, so we want to kind of bring some exponentials into it. So the very first thing we're going to do is we're going to just re-express this equivalently in terms of some exponential functions, right? So let's see what's going on here. Right. So what is this? So this is, you can just write this as, where did we get this? In case it's not clear. So this is x. Let's just look at the very first term. We'll just look at this times x, which is this thing, 1 minus x ln 1 minus mu, right? So this is this plus means that we can equivalently just write this as this product. Well, let's just look at this part right here. Well, this is the same as, you'll remember, this is the same as exp of ln mu to the x. And now the exp and the ln eliminate each other. So now this is again equal to mu to the x. So this section here is just corresponding to that. And then correspondingly, this chunk here will correspond to that. Okay, so that's where this expression comes from. We've just literally written this expression, our normal parameterization, but we've written it in terms of exponentials because we're kind of aiming at, getting some terms like that, getting an exponential and our parameters inside of it, and then some function of our data. So that's the very first step. So having done that, let's erase all of this to make it a little bit cleaner. Okay, so now what has he done next? So again, what are we trying to do? We're trying to get some parameters multiplying some function of the data. Well, it looks like we can actually already do that inside the exponential. So we've got an x term here. That's going to be our single data point. And there's another x term. So we can just write this as, what's going on in there as. So this is going to be equal to, this is x times x ln mu minus x ln 1 minus mu. And then we've got the remaining term, which is a ln 1 minus mu. And all of this is inside the exponential, right? So now we can just write this as x of ln mu of 1 minus mu. So that takes care of these components. And then the remaining term is the x times the ln of 1 minus mu. And that's just the x is going to be canceled by the ln. So you're just going to get, this is just going to be equal to 1 minus mu x blah, 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 which is precisely this thing here. Okay, so it's just some very simple manipulations to get the expression in the form that we need, which is this one. Okay, so let me erase some of the junk up here as well. Okay, cool. All right, so now we've got that. Now we're like, okay, it's getting a bit closer to the form that we want. So here, look, we've got our x is showing up, and now there is what's our eta? Well, this is a scalar, so it's not, the transpose is just going to be a simple multiplication. So if we just compare the terms, we see that our eta is just ln of mu 1 times 1 minus mu. So you see, like, we had this parameterization that maybe is more natural to us when we think about it, or we think about it just in terms of like the probability of the coin being heads or tails. But the actual parameterization that shows up, which we call the natural parameters, isn't quite that. It's some function. It's ln of mu 1 minus mu. So it's I don't know if those parameters are necessarily natural or not, but they're often not the ones you would think of right away as being the natural way of parameterizing the distribution. Nevertheless, to get into this form, we need to think about them in that way. Okay, so the natural parameter here is eta is ln of mu times 1 minus mu, and now we want to figure out these remaining terms that we need. So let me just re-highlight this here. Okay, so what else do we need? Well, we need g of eta, right? And our g of eta looks like, well, we have 1 minus mu, so we need to get that in terms of eta. So how are we going to do that? Well, we're just going to solve, we're going to determine what mu is in terms of eta. So we can express this in terms of eta rather than mu. Okay, so if we actually do that, it's easy enough and as an exercise for you to do that, to show that sigma eta is 1 plus x minus eta, and mu is going to be that sigma of eta. So this we've got this mu over here, and we've got 1 minus mu is going to be 1 minus sigma of eta, where sigma is kind of this logistic sigmoid function. And if you actually plot this out, what does it look like? Why do we get that? So as eta goes to let's just as eta goes to infinity, what's going to happen? Well, you're going to get 1 over 1 plus, this will go to 0, so this will tend to 1. As eta goes to minus infinity, this thing will end up being quite large, so then this whole thing becomes 0, so you end up getting, being at 0. And at eta equals to 0, you get 1 over 2, so about 1/2. So the function kind of looks like this, basically. So this is called the logistic sigmoid function. Okay, so what do we have here? So we might think, okay, well, you could kind of write it that way. We're basically done. So we can go back to our distribution here that we've re-expressed it. So we can write this as 1 minus sigma eta times x, all that good stuff. But equivalently, it turns out that we can actually simplify this even a little bit more, because this particular sigmoid function we can actually simplify, because, let's see, so 1 minus sigma eta is going to equal to x minus eta over 1 plus x minus eta. And then if you just multiply the top and the bottom by x of just positive eta, so this is then going to equal to 1 plus exp eta, right? And that's just the same as is going to, if we just look at the form, it just looks like sigma of minus eta. And the reason why the minus eta is because in the definition of sigma eta, there's a minus sign down here. So if we've gotten rid of the minus sign, then we need to apply minus eta to the sigma function. So that's all it is. So that's where you get the sigma of eta showing up over here, and you've got this parameterization now of our probability distribution in terms of the natural parameter eta, which is related to our kind of default, let's say our human parameters through this particular distribution. So let's highlight that actually, because I think that's quite important. So you see what we've done here is we've actually gone from a distribution we've gone from expressing the distribution in terms of our human parameters mu, which is mu to the x whatever, which is going to make sense from the the coin toss example. We've expressed the same thing, but now we've reparameterized and replaced our mu with eta. So now we've got eta showing up here, and now we've expressed it in a particular form. So now we've got this sigma of minus eta, and then the exponential function appearing. So now all we do is just to check off everything to make sure that it is indeed in the exponential family. We just look at the various terms. So let me just copy this down. So what do we need for an exponential family? Well, we needed something to be, there was an h of x, there was a g of eta, and then there was an exp eta transpose u of x, right? So that's what made it an exponential family. Well, if we just kind of compare these two things, what do we find? Well, we find that h of x is 1. So there is no term, there is no function just of x. There's just a one, except for the identity function, the 1 function. So that's where that is. U of x, so x is showing up by itself without any functions wrapping it. So u of x is just x. And g of eta, which is this function we need, that's a function of just of eta, is sigma of minus eta. So that's showing, it's kind of some simple calculations showing that okay, the Bernoulli distribution describing a coin toss is actually in this family. So now we're going to so that's all you need to do basically. So having done that, now we'll just try to do the same thing for the multinomial distribution. So that was kind of like you could use that to model the rolling of a dice, maybe a dice that's fair or not fair. What is the probability of getting a 6 or a 3 or a 2 or whatever it is? Okay, so let's start with that. So let's now talk about the multinomial distribution. That for a single observation x takes the form of this. So remember, we had the probabilities of each one of those things happening, and we had kind of a one hot vector, which was 1 for for whatever the case was that had actually occurred. We were encoding the rolling of the dice as a vector of, let's say, a binary vector of 6 elements with just one of them being on. And and that corresponding one, well, we'll get the corresponding mu, the probability showing up, and the rest will be set to 1. So this probability, you could express the probability of the dice again compactly in this way. And notice that this is, as we talked about when we talked about these distributions originally, this is a generalization of what we have here for the Bernoulli distribution, right? So this is, this would be, you could think of the Bernoulli distribution as like for a die that only has two faces on it. And so that's what we have. Okay. So for a single observation, remember, in this single observation, x is again, it's a vector because of that one hot encoding. Okay, where x equals x1 to, and I believe this should be because x, he needs to rename this. This should be m because he's got the k's going from 1 to m, I believe. Okay. Now for a single observation, takes the form so and so. And again, notice the very first step was we're going to apply this exponential function and just express this this product as a sum, so the exponential of a sum, and each one of these terms is just expressing mu k to the xk as an exponential. So this thing is just, mu k to the xk is going to equal to exp ln mu k to the xk, which is going to be exp xk ln mu k. And now because we're multiplying a bunch of them, we get the sum of a bunch of terms like that. So that's where that comes from. Oh. Okay, cool. Again, we can write this in the standard representation. P of x given eta is, we're again trying to get everything into this particular form, and it looks like we're basically done here, right? Because we've already got, we're basically finished. So here we've already got the x's showing up, we've got the etas showing up, and the etas, well, what are they going to be? Well, if we look at this term, it looks like that vector of etas needs to be ln mu of k. So that's it. So we're all done. So again, comparing with 2.194, which is this thing, we see that mu of x, so x is showing up by itself. So u of x is just x. H of x out here is just 1. So that's that. But also there's no additional term for the eta term. So g of eta is also 1. So that's kind of one representation of the multinomial distribution, showing that it is indeed in that family. Now, what's cool is we can now express it in a second way. So that's what he's going to talk about now. So note that the parameters eta k are not independent because the parameters mu of k are subject to the constraint. They have to sum to 1, right? These are the probabilities. So if I tell you 5 of the 6 probabilities, you know that the last one is going to be 1 minus that. So let's highlight that as well. I think it's important. So parameters are not independent because the parameters mu of k are subject to the constraint, so and so. Okay, so that given any m minus 1 of the parameters, the value of the remaining parameter is fixed. Now, in some circumstances, it will be convenient to remove this constraint by expressing the distribution in terms of only the m minus 1 parameters. So that's what we're going to do now. So instead of here we've got eta 1 to eta m, well, we're going to express it just in terms of m minus 1 parameters. So how are we going to do that? This can be achieved by using the relationship to eliminate mu of m by expressing it in terms of the remaining mu of k, thereby leaving m minus 1 parameters. So note that these remaining parameters are still subject to the constraints, so they have to be probabilities, so they all have to be between 0 and 1, and their sum has to be less than 1. It will be greater than equal to 0, but it has to be less than equal to 1, otherwise one of the probabilities is going to end up being negative, which we can't have. Okay, so now we're not going to actually use these constraints in the formulation, but they still have to satisfy it. Okay, so the game is going to be taking mu of m. Let's highlight that as well. So it's going to be eliminate mu of m by expressing it in terms of the remaining m minus 1 parameters. Okay, so it's going to be, again, a pretty straightforward procedure. Okay, so making use of the constraint 2.209, so that was this one. The multinomial distribution in this representation then becomes, so this is what we just started with. And now we're going to split it up, right? So this is m minus 1 terms, just so nothing fancy with them. And now this thing, so this is going to be, mu of m, right? And let me see where the other one comes from. So let's just work it out. So it's going to be the exponential of the sum on m minus 1 plus xm times ln of 1 minus sum m minus 1, k equals to 1, mu of k. Good, so that's what we have here. Oh, and I see, yeah, so I was confused actually. So I was confused with, like, where is this coming from? And the reason, okay, so basically, it's a one-hot vector, right? So we know that so this is just using, there's actually a good point. So x is one hot, which means that exactly one of the elements is going to be 1. So that means that their sum has to be equal to 1 when they're binary. So that means that we can write xm is going to equal to 1 minus sum on k equals 1 to m minus 1 xk, because, so this is, this holds if and only if the sum on k equals 1 to m, k equals 1. So that's just expressing that. So this was kind of a little bit, good that we stopped here, because that's where this comes from. So this is actually, so this is xm, and this, so this is mu of m. So this is because of the one hot aspect of the encoding. Okay, so that's kind of maybe the one tricky bit of this representation. Okay, and now that we've got that, again, remember what we're trying to do is we're trying to like have some terms, the exponential of x times some function of the parameters. Okay, so what we're going to do now in the next step is to group everything by whether it contains xk or not. So what do we have here? Well, it looks like we've got a sum of xk terms multiplying ln of mu k minus, again, a sum of xk terms. Each one of them is going to be multiplying this ln of 1 minus 1 minus this sum. And because there's a minus sign, we can just combine the natural logarithms, and so get mu of k showing up at the top, and then this term showing up at the bottom. And the final term that we have is just 1 multiplying this, which is contributing a final term that's just going to be a function of our parameters mu. Okay, so now, and let me clean this up a bit so we can see, we can get a better sense of what's going on. Okay, good. Okay, great. So now let's look at what we have. So we've got some xk's multiplying some parameters. Well, remember what what we were looking for. We're looking for eta transpose interacting with mu of x. So it looks like by just again matching this template matching thing, we've got that eta k is equal to ln mu of k so over 1 this sum. So that's essentially, we just look at the pattern we're looking for, and we've got the x's, we've got the etas, we're done. Okay, so now we now want to express so these are our natural parameters. So now we want to express mu of k in terms of the natural parameters, exactly the same as we're doing in the case of the Bernoulli random variable. So how are we going to do that? Let's just do a couple of steps of it. So the very first thing we're going to do is let's just exponentiate. He says, but first by summing both sides over k, then rearranging. So the way I did it was I just said first let's just exponentiate. So we'll get mu of k over 1 minus, I'm just going to call it the sum of mu, is equal to exp mu of k. And now what we're going to do is then we're going to sum both sides. So now if I sum on the top and the bottom, I will get, well, actually, the first step, we will get mu of k is equal to exp eta k times 1 minus the sum on mu, right? But we need, so what do we do with that sum on mu? Then we sum on both sides over k. So now we get sum on mu is equal to sum on exp eta k, so sum on mu of k, times 1 minus sum, okay, so then we kind of, then we got to rearrange. So then we get, well, sum on mu of k times 1 minus, sorry, it's going to be 1 plus sum on exp is equal to the sum on the exp. So then the sum on mu of k is equal to the sum on exp eta k over 1 plus sum on exp eta k. And I think you're getting the picture here. So you just kind of substitute that back in, and you end up with this expression. So that's basically what he means here by this summing on, by first summing on both sides. So you have to exponentiate, then do the summing on both sides, figure out. So first express mu of k in terms of the exponential of eta k, and then times 1 minus the sum on mu's, and then sum on both sides. Solve for the sum in terms of all these exponentials, and you will then end up with this expression. So let's highlight that. I'm going to erase all this stuff. Okay, so this is a good one to highlight. Very good. And indeed, and this is called the softmax function, which you might have heard about if you know, for example, work with neural nets. And the reason why it's called that is that you can imagine that if one of these, so what does the maximum function do? Well, the maximum function kind of indicates you have like a vector of values, and you want it to indicate which one is the largest. And so this function kind of does that in a soft way. So rather than making the maximum one exactly equal to 1 and all the other ones 0, so indicating it perfectly, it kind of gives each position in that vector a value related to what, you know, how close it is to being the maximum or not. And the way it works is that basically this exponential function is going to magnify the magnitudes of the elements in this vector eta. So basically, if you got this, you know, eta 1 all the way to, you know, eta m minus 1, imagine if kind of one of them is very large. Then when you exponentiate it, well, that exponential is going to be, again, it's going to magnify the difference between that largest value and the rest. And then when you divide it by 1 plus, you know, that sum, it will then, it's basically going to dominate that sum as well. So it will end up, you know, you'll get a bunch of small values and a very large value coming from that exponential being divided by essentially that same very large value, because all those other, you know, all those other terms are actually going to be very small. So then you will get a value that's kind of very close to 1 at the location corresponding to the largest element of eta. So that's kind of just a little bit of intuition about why it's called that. This is called the softmax function or the normalized exponential. In this representation, the multinomial distribution therefore takes the form so and so. So let's have a look at this. So we've got what do we have? So we've got the x of the eta multiplying by x, and we've got our eta defined up there. Let me highlight that too. So that's cool. So again, you know, look at this parameterization. Again, not the human parameterization, it's the natural parameterization. The natural parameterization for the exponential family. And then let's see where this particular term comes from. Well, right. So that was, where was that coming from? Well, that was just coming from this guy right here, right? So this was going to be, you know, the exp times the ln of 1 minus m minus 1 k mu of k. It's going to and 1 plus the sum on x eta to the k is going to be okay, right, yeah, so it just basically comes from this expression here. So if we take the sum on mu of k, well, then this is going to be equal to the sum on exp eta k over 1 plus the sum on j exp eta j. And then 1 minus that sum is just going to equal to 1 over 1 plus sum of exp eta j. So that's 1 minus the sum of that. And then you've got the exponential multiplying the ln, so it just eliminates it. So basically, so we get 1 minus sum on mu of k is just going to equal to 1 plus sum on exp eta, you know, whatever, to the minus 1, which is where this comes from. Okay, so you should just be able to go and verify. So so this term is coming from x times ln of this, so it is just this particular, you know, it's the 1 minus, basically it's the mu of m that we had, and we can express it in terms of our etas using this expression and essentially solving, you know, forming the sum and then getting 1 minus it, and you end up with this. Okay, cool. So, again, it's kind of lots of these little manipulations, but they're all, quite, basic and pretty straightforward. I think the only tricky one that required us kind of to remember some definitions. It wasn't mathematically tricky, we just had to remember, how do we express x of m? Well, it was just using the one hot property. So I think that's the one bit that you'll need to remember. Okay, and so now it says this is the standard form of the exponential family with parameter vector eta is equal to eta 1 to eta m minus 1. So it actually is a vector now. U of x, again, look, it's just showing up all by itself. H of x is equal to 1. And this normalizing factor, there's a term that has to do with, it just contains eta. Well, it's just this thing right here. Okay, so again, that's just showing that there's even two parameterizations that of the multinomial distribution, and showing that putting them both in the exponential family. So that's pretty cool. So it's not necessarily the case that there's just one way of expressing a probability distribution in the family. In this particular case, we've shown two. One of the things I thought was actually quite interesting, and maybe makes some sense, is that when we like our parameterization here is a little bit simpler, right? So we've got this kind of additional dimension, this mth dimension of the mth data point, and so now that means that one of our parameters isn't actually independent. This depends on the other ones. But what we gain in return for that is this simplified form of the normalizing constant and the normalizing function. Whereas when we try to compress things a bit, we're trying to say, okay, no, actually I want to express things with m minus 1 parameters because I know that the mth one is 1 minus the sum of the others. Well, we can still do that, but now kind of we pay a price in that our normalizing function becomes a little bit more complicated. Although the term in the exponential still looks the same, but we have one fewer parameters, and it seems to kind of make life a little bit more complicated. So I thought that was kind of an interesting point. Okay, and the very last one, which is going to leave as an exercise, which you guys should definitely try, is the Gaussian distribution. So again, let's just look at it. So for the univariate Gaussian, here is our distribution that we have. And again, notice, so now we're going to expand it out. We've already got an exponential thing doing some of the work, so we didn't have to convert anything. There was no lns coming in. So now we've got the x squared term, we've got an x term, and then we've got a term that just depends on the parameters. And which he says, which after some simple rearrangement, which you guys should definitely do, can be cast in the standard exponential family form. With now, again, look at this, like the parameters, the natural parameters aren't our human parameters. So it's not even, we've got something, some function of the precision, but it's not even the precision, it's kind of the negative precision, right? The negative half of the precision, or I guess that would be, yeah, negative half of the precision. Interesting. And then it's not just the mean, but the mean normalized by the variance, or the mean times the precision. So again, human parameters and natural parameters are quite different. Notice also now our function of x. So the data is x and x squared showing up there. So kind of a nonlinear function of our data point. H of x all of a sudden is now appears. There it is. And now we've got a function of our parameters, this normalizing function, which has this particular form now. So again, it looks a little bit different from our kind of default parameterization, which is quite interesting. So have a go at that exercise. It's exercise 2.57. It'll just give you practice for how to kind of do these rearrangements. But basically, that's all it is. So it's just a matter of massaging your distribution into the form that we need it to be, which is this one basically. Cool. Okay, so I think that's was just a couple of examples of how we can show that some of the basic distributions we work with are members of this family. So in the next video, we'll just go on and we're going to talk about some of the other interesting properties of the exponential family when it comes to, maximum likelihood estimation of the parameters. So hope you've learned something in this video, and I hope I see you in the next one. Thank you.